And another edition of some physics. All right. So this is about magnets and magnetism. Great meme there because, magnet for you. Ha. Okay. So with no further ado, have a lot of questions to answer on this one. Nothing super difficult, I don't think, but a lot of topics. So we're going to go through what's magnetism, what are poles, what are magnets and magnetic fields, how does a compass basically work, what makes a magnet be a magnet, how does it work, what different kind of magnets are there, and a number of vocabulary things like magnetism, poles, and fields. All right. So a lot to go through, probably go through pretty quickly. So pause me, rewind, whatever you need to do to stay on top of this. As a reminder for my class, please take notes, upload them, show me that you're doing them for extra credit. And you don't need to write down every single word that's on here, but it's a good skill to have that you're just writing some of these things down to make sure that you are getting them into your brain, but also that you can refer to them when you've got some questions here in a moment. All right. So let's get down to the basics. What's magnetism? So magnetism is one of our forces of repulsion and attraction. We've seen that with electricity, and magnetism has some similarities to that. Now, what's going to cause it, and we'll get to this later, is the motion of the electrons in the object. Again, this is kind of why it relates a little bit to electricity, because electricity is movement of electrons. But magnetism is a little bit different. It's a force extending out, and it has to do with something else the electrons are doing. We'll get to that shortly. Um, Lodestone is a rock basically that's was one of the earliest known things that has magnetic properties to it. And we later found out that it's got a mineral in it called magnetite, and the magnetite has a lot of iron in it. And we'll see in a moment. Iron is one of the things that that often, if something is a magnet, that it's going to have a lot of iron in it. People figured this stuff out because things that had a lot of magnetite in them would move. They would point to the north of the Earth if given a chance to rotate, which was probably pretty freaky a couple thousand years ago that rocks would move. Everything has the ability to be magnetic, but again, like a lot of things like gravity, sometimes the amount is so small that it's not perceptible. Again, like me and this computer, there is a force of gravity between us. It's really too small to notice. All objects technically have magnetism, but most are too small to notice. When researching a little bit of stuff, I did, and you can Google this or find the video on YouTube. Some scientists at one point, they used magnetism to make a frog float. So basically, everything can be magnetic, but most of the time it's so small we don't really notice. Second question, poles. When we talk about magnets, we talk about poles. Up until this point, most everything has been pluses and minuses, positive and negatives. And magnets are similar to that, and they have these opposite things, but we don't call them pluses and minuses. We call them north and south. And these are kind of the opposite ends of a magnet. So every magnet, we've got two different versions down here, are going to have a north pole and a south pole. And this has to do with the direction in which some of the forces are coming out of it. And we'll see some drawings of that shortly. So there's a north pole, there's a south pole. Again, just like electric things, opposites attract, likes repel. So if you put the north pole to another north pole, they're going to push away. If you put a north pole to a south pole, they're going to snap together. And we saw some of the magnets in class do that the other day. If you break a magnet in half, it's not a north half and a south half. It ends up just being two small magnets, and it has to do with the direction. So if you looked at the picture that's on here with the north-south magnet, if you drew a straight line all the way through, kind of the idea is that there's an end of the arrow and there's a tip of the arrow. So if you break it in half, you basically make then two arrows, and they're both still pointing in the same direction. So you still have a north pole and a south pole. You have two smaller magnets. Is the Earth a magnet? Yep, the Earth is a giant magnet, and one of the reasons why is because the core of the Earth has a lot of iron in it. Effectively, the Earth is a giant magnet, which is why the ancient folks, when they found the rocks that moved, it was moving in response to the Earth's magnetic field. And because of this, there's an invisible magnetic field surrounding the Earth. We'll get to fields in a moment. For all planets, for that sake, and the sun, they all have magnetic fields. And this field extends out beyond the surface of the Earth, so even into space for a while. The Earth is basically a big magnet. Fun fact, North Pole is actually a South Pole. The reason why is because if you've got a compass, the North Pole of the compass is what's pointing north, but norths don't attract norths. Norths and souths attract each other. So effectively, if you have a magnet and we call the north part of the magnet the part that's pointing north, it's actually pointing to the South Pole, the magnetic South Pole. So the magnetic South Pole is at the geographic North Pole. Confusing. I know. What the heck is this magnetic field thing? All right, so a field, as it sounds like, is something that extends out. And so it's the area around a magnet where the force can still be felt and where the force extends. So you got a bunch of pictures down here, and these little gray lines are kind of showing where the field would exist around a magnet. So if you had a north-south bar magnet like we saw a minute ago, there's little spaces out here of attraction and repulsion. And the way that you interpret this is to imagine if you put the north part of a magnet in the field, where would it go? So again, like if you put it right here near the north would be repelled by the north, and so it would get pushed away. If you put the north over here on the other side, it would get pulled towards the south. If you put it over here on the side, it would get pushed away from the north and pushed towards the south, and would kind of move in this direction. These arrows show the direction that a north charged magnet would move if it was placed into this field, and it's always going to move away from the north and into the south. All right, so you can note these different drawings and how they kind of arrange. Again, going back to this, if you had two norths together, everything gets repelled away. So that's how you could easily tell that these are the same poles, north-north or south-south. If you have opposites, they're going to be connected, and the arrows would show you which way it's going. Again, it's always going away from the north, and it's going into the south. Compass. You may have seen these before, might have even handled one. Effectively, it's just a baby magnet, and it's able to rotate. And since it's able to rotate, it's going to use the Earth's magnetic field, and it's always going to point towards the North Pole. So the North Pole of this magnet is going to point to the magnetic South Pole, which is north. And no matter which way you move it. So if you spin it around, it's still going to point. If you move around, it's still going to point in the same direction. So this was an ancient way for people to be able to navigate, and people still use them to be able to navigate. Why is something magnetic? All right. There's a few reasons why. So oftentimes it depends on what's in it. There's three elements on the periodic table that happen to be side by side, 26, 27, 28, iron, cobalt, and nickel. And these are things that tend to become magnetic because of the way their atoms are put together. Some of our magnets can be permanent. Some of the magnets can be temporary. And if you know what those words mean, then you probably understand what that means. It means that a permanent magnet is always going to be working as a magnet. If it's a temporary magnet, it may kind of wear off over time. You can turn something into a magnet, but over time it kind of unmagnetizes itself. So the reason why something's magnetic, going back to those electrons, is because electrons, believe it or not, apparently they spin. And in a lot of different things, they spin in different directions and in orientations. And if you imagine them spinning and having like a North Pole and South Pole, sometimes you might have North Poles this way, North Poles this way, North Poles to the left, North Poles down. And all that spin kind of cancels each other out. And so something's not magnetic. But there's certain things that when they have electrons in them, if they're all spinning kind of in the same way, remember, every electron is a magnet. And so each of them has a little tiny magnetic force. But if they're all pointing in the same direction, that little tiny bit of magnetism kind of gets multiplied, right? And so that's when we see that an object actually becomes magnetic. This illustration down on the bottom right is one of the things that we see of understanding why something is magnetic or why it's not. If you look at all these arrows on the right, they're basically all pointing in the same direction with a few exceptions. And so each of these little kind of look like cells in a body. These are in physics with magnets, we call these things domains. So within a domain, you would have a bunch of spinning electrons. And in the domain, they were kind of all spinning in the same direction. And you'll notice on the left-hand side, these arrows are pointing in all kinds of ways. So some things are magnetic this way, some are magnetic up, some are magnetic that way. So it's really overall not magnetic at all. It's like everything kind of cancels out. But on the right, as everything is pointing to the right, they kind of all join forces and kind of exert a force in that direction. And that's going to be kind of probably pointing to the North Pole of whatever object this is. And this will be something that will be magnetized. So when we see the word domain, that's simply talking about a cluster of atoms or cluster of electrons in an object. And we get the domain spinning and pointing in the same direction, then the object can become magnetized. Now, we can actually make a magnet, right? How do we make a magnet? So we can take an object and make it a permanent magnet by using another magnet, basically. The idea is if something's not magnetic, we go back to this. So something on the left might not be magnetic, but it has the ability to become magnetic if we put it in the area of something that is magnetized. Now these arrows may all get pulled and kind of directed so they're all lined up the same way. All right. So a magnet can become permanent. Sometimes you can do this, but it doesn't last very long. So that's kind of a temporary thing. We can do this by contacting it with a magnet. Another word we used before with electricity is induction, which is you just kind of get it close and it kind of starts pulling things in the right direction. And you can also use electricity to be able to make a magnet too. Magnets can become broken, basically. You can demagnetize things. If they get too hot, if you bang on them, hammer them, drop them, those domains that are all pointing in the same direction can kind of get, with the energy given to them, kind of get knocked out of whack, and the object doesn't become, is no longer a magnet. All right. So that was a lot. We hopefully answered all these questions about what's magnetism, what are poles of a magnet, what's a magnetic field, and how can we interpret them, how does a compass work, why is a magnet in the first place, like what's going on the inside of it, and some things about different types of magnets there are. All right, so those are all of our basics. Hope you got through all that. I know I went through it pretty quickly, but that is it. Take care.